Imagine waking up in a universe where the fundamental laws of physics fluctuate unpredictably. One day, gravity holds you firmly to the ground, the next, you float into the sky. Atoms no longer bond properly, stars flicker out of existence, and the structures of reality break down. Such a universe would be chaotic, making life as we know it impossible. Yet, our universe operates with an extraordinary level of consistency, governed by unchanging principles that dictate the behavior of matter, energy, and spacetime. These principles are encoded in what we call universal constants. Universal constants are nature's immutable numbers, the fundamental values that shape the cosmos. They determine everything from the force of gravity to the speed of light, from the structure of atoms to the very existence of life. If even one of these constants were slightly different, the universe as we know it might not exist at all. But how did scientists discover these constants? Why do they take the values they do? And could they ever change? These questions drive some of the deepest inquiries in modern physics. One of the most famous universal constants is the speed of light in a vacuum, denoted as c, which is approximately 299,792,458 meters per second, or about 186,282 miles per second. This value is not just a measurement, it is a fundamental limit that governs the entire structure of spacetime. In the 19th century, physicists believed that light traveled through a medium called the luminiferous ether. However, in 1887, the Michelson-Morley experiment demonstrated that there was no ether, light always moved at the same speed regardless of the observer's motion. This led Albert Einstein to develop his theory of special relativity in 1905. According to Einstein's equations, the speed of light is the ultimate speed limit of the universe. No information, object, or even gravity itself can travel faster than light. This concept is foundational to modern physics, influencing everything from time dilation, where time slows down as one approaches the speed of light, to the understanding of causality. If c were even slightly different, the nature of time and space would be profoundly altered. While the speed of light governs relativity, another universal constant determines the structure of the universe on a cosmic scale, the gravitational constant, denoted as g. First introduced by Isaac Newton in the 17th century, g appears in his law of universal gravitation. It defines how objects attract one another through gravity, and its value is approximately 6.674 times 10 superscript 1 superscript 1 cubic meter kg superscript 1 s squared. The value of g plays a critical role in the formation of stars, planets, and galaxies. If it was slightly weaker, gravity wouldn't be strong enough to pull gas and dust together to form celestial bodies. If it was stronger, stars might burn through their fuel too quickly, making long-lived, life-supporting planetary systems rare. Interestingly, gravity is the weakest of the four fundamental forces, about 10 cubed, 6 times weaker than the electromagnetic force. Why is gravity so feeble compared to the other forces? This remains one of the greatest mysteries in physics. Some theories suggest the presence of extra dimensions, where gravitational effects leak into unseen realms. At the opposite end of the scale from gravity, we enter the quantum world, where the behavior of particles is dictated by another fundamental constant, Planck's constant, denoted as h. Discovered by Max Planck in 1900, h defines the relationship between the energy, E, of a photon and its frequency, f, through the equation E equals hf. Its value is 6.626 times 10 cubed 4 joule-seconds, an unimaginably small number that determines the discrete, quantized nature of energy in the universe. If h were different, atoms would have entirely different energy levels, potentially altering the way chemical reactions occur. Planck's constant is a cornerstone of quantum mechanics, influencing everything from the Heisenberg uncertainty principle to the structure of the atomic nucleus. Without it, the universe might not have stable matter at all. Among the many universal constants, one stands out as particularly enigmatic, the fine structure constant, denoted as alpha. It is a dimensionless number with an approximate value of 137, governing the strength of electromagnetic interactions. Physicist Richard Feynman once called it one of the greatest damn mysteries of physics. If alpha was slightly different, atoms might not form properly, affecting everything from molecular chemistry to the structure of stars. Some theories propose that alpha may have changed slightly over cosmic time. If confirmed, this could revolutionize our understanding of physics. One of the most profound questions in physics is whether these constants are truly constant. Could the speed of light, gravity, or quantum mechanics have been different in the early universe? Studies of distant quasars suggest that alpha may have been slightly different billions of years ago. Similarly, some cosmological theories propose that G could evolve over cosmic time. If this is true, it could hint at deeper, underlying laws governing the universe. Scientists use atomic clocks, spectral analysis of ancient light, and particle physics experiments to test the stability of these constants. While no definitive changes have been detected, the possibility remains tantalizing. Why do universal constants take the values they do? This question leads to two intriguing possibilities. The first is the anthropic principle, the idea that the constants of nature are what they are because they allow life to exist. If they were different, we wouldn't be here to ask the question. The second possibility is that a deeper theory of everything may explain why these constants have their specific values. Some physicists believe that a unified theory, potentially involving string theory or extra dimensions, might hold the answers. Universal constants are more than just numbers, they are the scaffolding upon which reality is built. From the cosmic speed limits set by c to the quantum mysteries of h, these constants dictate the fundamental behavior of the cosmos. As scientists probe deeper into the nature of these constants, we may one day discover new principles that reshape our understanding of reality itself. Could the laws of physics be different in other universes? Could these constants shift over time? The answers remain elusive, but one thing is certain: the more we explore, the closer we come to unlocking the ultimate secrets of the cosmos. Stay curious, and keep exploring with Discovery 2.0.